Hello students, welcome to this lecture in which we'll start by talking about continuity of piecewise functions. The first example that we're going to do is to show that absolute value of x is continuous everywhere. So before we defined absolute value of x as x when x is greater or equal than 0, or negative x when x is less than 0. But for the purpose of this lecture, it might be more useful to take x equals 0 and put it as a separate value. So we'll say that it's x when x is strictly greater than 0, it's 0 when x is equal to 0, and it's negative x when x is less than 0. So again, we just took this specific value 0 and put it as a separate piece because it would be a little bit more useful for this particular exercise. So basically, we're saying that absolute value of x is the same as x on the interval from from 0 to positive infinity, and is the same as as maybe here we can insert as the polynomial x over here, and is the same as the polynomial negative x on the interval from negative infinity until 0. And we know that polynomials are continuous everywhere, but polynomials are continuous everywhere. So x equals 0 is the only possible discontinuity of absolute value of x, right? Because x itself is continuous, negative x is continuous, so this is the only place we have to look for discontinuity. And we know that absolute value of 0 is equal to 0. So to prove continuity at x equals 0, we must show that the limit exists, right? We must show that the limit of absolute value of x when x approaches 0 is equal to 0. That's the only thing left to show. And because the formula for absolute value of x is piecewise, and changes at x equal to 0, we will consider piecewise. We will consider one-sided limits. One-sided limits at 0 rather than one-sided limits. All right, so piecewise function, so we use one-sided limits, means we're going to calculate limit when x approaches 0 from right of absolute value of x. And remember, when we approach 0 from right, that means we take numbers that are positive, and according to the formula, absolute value of x is x. So it's going to be limit of x as x approaches 0 from right, which is equal to 0. And the limit of absolute value of x when x approaches 0 from left. So we're going from left, so we take negative numbers. And when inside of the absolute value we have negative numbers, we have to put an extra minus. Up front. So we're going to get limit extra minus x. X goes to 0 from left, but we still get 0. And since the limit from the left is equal to the limit from the right, the limit of absolute value of x when x approaches 0 is equal to 0. So check mark. Conclusion, absolute value of x, this implies, is continuous at x equal to 0. And so we're done with this example. So in our next example, let's try to see whether the function f of x which is equal to 2x plus 3 when x is less or equal than 4, in 7 plus 16 over x when x is greater than 4. Find the intervals where f of x is continuous. All right, so we have to find the intervals where this function is continuous. So we have two pieces. Let's look at the case when x is less or equal than 4. Or let's do the case when x is strictly less than 4. It's going to be a little bit easier. When x is strictly less than 4, we have f of x equal to 2x plus 3, which is a polynomial. Maybe we can include the 4 here. Let's include the 4. It's a polynomial function which is continuous everywhere. So polynomial function, so it is continuous. On minus infinity to 4. All right. Again, I'll exclude 4, so that will be a little bit easier. So when we're in the case when x is greater than 4, we have f of x equal to 7 plus 16 over x. 7 is a polynomial. 16 over x is a rational function, so it is continuous on its domain, and so domain is x is not equal to 0 for this function, but we're in the case when x is greater than 4. So 7 is continuous. 16 over x is continuous. And we have the theorem that says the sum of two continuous functions is continuous. So 7 plus 16 over x is continuous on x greater than 4. Maybe not on, but 4. So now the last case when x is equal to 4. That's the only place where we might have discontinuity. And again, we have to use left limit and right limit to figure it out. So limit when x approaches 4 from right of f of x. So we approach 4 from right, so we're greater than 4. And our function is going to be 7 plus 16 over x, because when x is greater than 4, we have to use this piece over here. So we say limit of, oh, forgot the word limit of 7 plus 16 over x when x approaches 4 from right. Right, so we can use direct substitution. We can just plug in 4, so our answer will be 16 over 4 plus 7. So it's 7 plus 4, which is 11. That's the limit when x approaches 4 from right. And then we have to do the limit when x approaches 4 from left. So we're going to approach 4 from the left side. So our number will be a little bit smaller than 4. And when the number is a little bit smaller than 4, we have to use 2x plus 3 for our function. So it's going to be the limit of 2x plus 3 when x approaches 4 from left. So we plug in 4, so we're going to get 8 plus 3, or maybe write the whole thing, 2 times 4 plus 3, which is 8 plus 3, which is 11. Conclusion, the limit of f of x when x just approaches 4, since the limit from the left is equal to the limit from the right, we get 11, so check mark. F of x is continuous at x equal to 4. Thus, f of x is continuous everywhere on minus infinity to infinity. So we've done these two examples for the continuity of piecewise functions. And the next idea is to talk about continuity of composition of functions. Again, important idea, will help us a few times in the future. So the first rule for this says the following. The first rule says that if a limit when x approaches c of g of x is equal to L, and if the function f is continuous at L, then limit when x approaches c of f of g of x is equal to f of L. So to explain what it means, let's write it like this. We say that the limit of f of g of x when x approaches c is equal to f of the limit of g of x when x approaches c is equal so is equal to f of L. Right, so basically what it says, we can take limit and we can bring it inside if f is continuous. If f is continuous. Right, then it works. So this equality remains valid, if limit when x approaches c is replaced by one of the following. Of limits one of the following. So limit when x approaches c from the right, limit when x approaches c from the left, limit when x goes to positive infinity, and limit when x goes to negative infinity. So the same theorem would be true. Right, and one special case that is interesting, f of x is equal to absolute value of x. Since absolute value of x is continuous everywhere, we have limit of absolute value of g of x when x approaches c is equal to absolute value of the limit of g of x when x approaches c, provided the limit of g of x when x approaches c exists. So for example, we have limit of 3 minus x squared when x goes to 3. Let's say 2. When x goes to 2 is equal to the absolute value of the limit when 3 minus x squared when x goes to 2. So we have, when we plug in 2, 3 minus 4 will be negative 1. So absolute value of negative 1, which is positive 1. And the last theorem for this continuity piece is this one. Theorem says that part A says if the function g is continuous, at c, and the function f is continuous at g of c, then the composition f composed with g is continuous at c. And part B of the theorem says that if the function g is continuous everywhere, and f is continuous everywhere, so if both functions are continuous everywhere, that their composition is continuous everywhere, then the composition is continuous everywhere. Continuous everywhere. All right, so to finish this discussion, we have to talk about the intermediate-value theorem, and we're going to use it this semester. So this theorem tells us, and it has a name, it's called Intermediate-Value Theorem. Intermediate-Value Theorem. All right, and for shortness, it's usually called IVT, Intermediate-Value Theorem. So it says the following: if f is continuous, on a closed interval from A to B, and K is any number between f of A and f of B. And at first it doesn't make sense, but then we'll see graphically, and it's inclusive, so it could be one of the endpoints. From the picture, it will be clear what I mean, right? Then there exists a number x in the interval AB such that f of x is equal to k. So let's look at it. Geometrically. Geometrically, we have a continuous function from A to B. So some kind of a curve going from A to B. And this is f of A over here. And this is f of B over here. So if you choose any number in between, let's say k, this theorem says there is at least one number such that f of x will be equal to k. In our particular case, we have few numbers. We have number here and number here, so we have few of them, but the theorem guarantees that there is at least one of them there. So this is a good place to stop this lecture. We're done with the continuity idea. And we learned limits, we learned continuity. It's time to go back and talk about derivatives. So I'll see you in the next lecture.